For example number 2, we're going to calculate the pH when each of the following solutions are added to 100 milliliters, and there's a period after that. That means all of those are significant digits. So 100 decimal place is 3 significant digits. 100 milliliters of 0.10 capital M molar HClO. Now, HClO is hypochlorous acid, and it has a Ka of 4.8 times 10 to the negative 8. And the pKa was already worked out for us, 7.4 over here. I'm just going to write that down right here. Now, first, we're asked to calculate the pH when 0 milliliters of sodium hydroxide are added. So when there's 0 milliliters, that means all we have is a weak acid problem. No base has been added. So we just work this as a weak acid problem. So I put my initial concentration. I have no H plus hydronium ion or hydrogen ion. I have no conjugate base. I'm going to change by some value X that I don't know yet, but I will find it. And then I have my equilibrium. So I put in those items, the equilibrium items, for my Ka expression. So I have x squared on the numerator and 0.10 minus x for the denominator, and that equals 4.8 times 10 to the negative 8. Now notice how our initial concentration is more than 10,000 times different than our K value. That means we can simplify, because that means that x value is going to be relatively small in comparison. So I multiply both sides by 0.1, and I get a value of, so then we have x squared equals 4.8 times 10 to the negative 9. I take the square root of that, and I get an x value of 6.9, I would round that to 6.93 times 10 to the negative 5. Now the unit is capital M molarity, and this x is equal to the concentration of the hydrogen ion. We were asked to find the pH. So I type log and answer in my calculator, and I get a pH value before any base is added of 4.16. Now we're going to add some base, and I think we were going to add, example 2 is what we're working on, 75 milliliters of a 0.1 molar solution. So 75 milliliters of a 0.1 molar solution, so that's 0.10 moles per liter. But my acid volume, I had 100 milliliters, so 0.100 L times 0.10 mole per liter. So moles of acid to start, I have 0.1 times 0.1, or 0.01 moles of acid to start. For the moles of the base, I take my 0.075, that is the volume of the base converted to liters, times the concentration of the base, and I get 0.0075 moles of base. Now, because my moles of acid is greater than my moles of base, I am before the equivalence point. So I'm going to roll down here a little bit. So the moles of acid, the excess moles then is going to be my moles of acid minus my moles of base, and you're going to ignore these significant digit errors here. You can just assume this. It's accurate, but 0.075. I'm just trying to keep things as straightforward as possible. So we have, I need another 0. So we have 0.0025 moles of acid in excess. This is after the base has been consumed. Now, remember, when we have our weak acid and we're reacting it with a strong base, we have a one-way arrow and we are making water and conjugate base. This is a 1 to 1, 1 to 1. So whichever is the limiting reagent here, which is the strong acid, those number of moles become the number of moles of conjugate base that are made. So excess moles of acid here, I'm just going to fill in 0.0025 moles of HA after consumption. The moles of the base are then 0.0075. So now I can find the pH at this point. And I'm going to do that by using the Henderson-Hasselbalch. pH equals the pKa, which I wrote down earlier, 7.40, plus the log log of the A minus, the ratio of the conjugate base, to the weak acid. Now, I can use moles in the Henderson-Hasselbalch equation. I don't have to convert that to molarity. 2.5. And I get a pH at this point of 7.8. I actually get 7.877. I would round that to 7.88. So after 75 milliliters of base, I would get 7.88. And prior to that, I had 4.16. Now at 100 milliliters of base, so my concentrations are the same, so that's going to be at the equivalence point. Scroll down here, so the moles of the acid will equal the moles of the base. So if I subtract them, I'm going to get 0. And that is because I have 0.01 moles of both the acid and the base. Now, the moles of the base are going to be equal to the moles of the conjugate base, and that is simply stoichiometry. So the moles of the conjugate base are going to be 0.01 mol, moles of A minus. And see how I highlighted that in yellow? Because I wanted that to go down here as well. What we need to do is find the new molarity, the new concentration of our conjugate base, the A minus. So we need the total volume of solution. Well, if we had 100 milliliters of each, and I need to verify that because all of a sudden that doesn't feel right. So we're working on number 2. 100 plus 100. Yep, I have 200 milliliters of solution. I need to convert that into liters. So 0.200 L liters gives me the new molarity, or the molarity of my conjugate base, 0.05. And if we were paying attention to significant figures, you would need 2 zeros after that, capital M. So that value is going to go here. Now, because everything is dependent on the A minus at the equivalence point, we need to find the KB value. KB is related to Ka because Ka times Kb is equal to Kw. So because Kw is a constant, and we have our Ka, which just escapes me at the moment. Come up here. 4.8 times 10 to the negative 8. Then we can calculate our Kb. Now make sure you're putting this into your calculator correctly. And I get 2.08. So this was 4.8 times 10 to the negative 8. So Kb is 2.08 times 10 to the negative 7. Now I have no HA and no OH minus at this point, but I will reestablish this equilibrium. And when I do so, these are going to be my concentrations. So all of that, I need to put everything into my Kb expression, which will end up being x squared over 0.05 minus x. Now, because my initial concentration, 0.05, is more than 1,000 times different than the Kb, I can simplify this. So I multiply both sides, 2.08 times 10 to the negative 7 times 0.05, and I get x squared is equal to 1.04 times 10 to the negative 8, but I'm not done. I need to take the square root of that so that I get my x equals. I need x by itself. So that's 1.02 times 10 to the negative 4, capital M, molarity. I don't know what happened there. So X is the concentration of the hydroxide ion this time, not hydrogen. Now, you can solve for POH because this value is already in your calculator, so why make it hard? And POH, I get 3.99. So to solve for pH, it's 14 minus POH, so I get a pH value of 10.0 for this question. So when no base is added, there's a pH of 4.16. At 75 milliliters, it's 7.88. And with 100 milliliters, it's 10.0. Those are the pH values.